Okay, so good afternoon and welcome to our online version of STAT 332. So hope you're all doing well and healthy as we navigate the rest of this term together. So I will be monitoring chat, and I think it looks good. People can hear me, so let's get right on it. So first, I would like to begin with, so first let's go here. And so the topic today that we need to cover is randomized block design. So let's set this up here. So randomized block design. So we're taking the model that we looked at a little while ago, where we had multiple treatments, and we were looking at contrasts and ANOVA. And so today we're going to extend that a little bit and put in blocking. So I'll first give you an example, and then we will go through the concept. So randomized block design. Okay, so to motivate this section, I'll start off with a little example. An example from some of the work that I do myself is in regards to the strength of wood. So suppose to illustrate, we head down to Home Depot and we want to pick up a few pieces of 2x4s for the purpose of an experiment. And so we see, for example, there's like different there's different prices of 2x4. So suppose we have here like a $10 version, a $20 version, and a $30 version. Okay, so these are the prices. Okay, so we're going to suppose we go down and we want to do a small pilot study. So I go and buy 5 pieces of each. Okay, so we have 5 pieces. And I do the same for the other 2 price points as well. In the engineering world, these would be called different grades of lumber, and generally, well, why does wood sell more? Well, it's because they're likely also to be stronger pieces. And so we want to do our experiment to make use of wood that varies across the strength spectrum. So that's why if I'm setting up this experiment, it makes sense for me to go down and buy wood from different grades. So suppose here I have 5 pieces. Now, the key thing I want to do an experiment on here is the question is, so the question that I would investigate with this, with these small pilot samples is to ask how does pre-stressing wood affect the strength? Okay, so to do that, I'm going to choose a few different load levels. So so suppose I'm going to try let's say a few different load levels. Let's say 1,000 load. Let's do 3,000, 5,000, 7,000, and 9,000. Okay, so I'm going to do an experiment where I pre-stress my specimens according to these loading levels, and the key idea here is to investigate how the loading level affects how strong the piece of wood is. Okay, so that is the setup. Okay, so as we've learned, so now there's one factor here, and that is in this experiment, and that is the load level that I'm going to apply to the wood. And so I've set it up here such that we have 5 levels. And so as we've learned from doing randomization, well, I should assign these 5 load levels, which, because there's only one factor here, these are also called treatments. Okay, so these are the 5 different treatments, and I'm going to assign these treatments at random to my sample specimens. Okay, so now, if I told you I just had 15 pieces at random, then generally what would we do? We would do the completely randomized design. We would randomly assign 3 pieces to each of the 5 load levels, and I would have a balanced design, completely randomized, and we would investigate differences between these 5 treatments, whether there are any differences among any of the treatments, and if we want, we can also ask whether there are contrasts between different treatments combinations. Now, the only new thing that I threw in here is the fact that I have 3 different quality of wood. Okay, so remember at the outset I set it up such that we have 3 different price points, so 10, 20, and 30. Now, so where does this blocking come in? So if you've been following along, naturally, what is the blocking variable here is to use the quality of the wood as the block. Okay, now why is that a sensible thing to do? Well, I know because of the way the wood is priced, I know in advance that the 30 quality wood is probably going to be stronger overall than the 10 quality wood. Okay, so I already know there's a lot of variability in the strength among these 15 pieces. These 5 are probably going to be quite a bit weaker than these 30. Okay, so how then can I tell whether there's a difference between these 5 different loading levels? Is to use blocking. Okay, so there are many things that can affect the strength of each piece of wood, and one very important one is this grade classification. Okay, and so the quality of the wood inherently affects the strength of each piece, and also, of course, the treatment that I'm going to apply, which is these 5 different load levels, also would affect the strength of the wood when it's tested. Okay, so therefore, by blocking, treating these 5 of the lowest price as a block, I would want to assign these 5 load levels at random to these 5 pieces. Okay, and so that's where the randomization comes in. We randomize the application of the treatment within block so that we can control for the block-to-block variability. We know strength will get stronger as we go from cheap to expensive, and we also want to see within each block how the strength changes also as we go from 1K pre-stress to 9K pre-stress. Okay, and so here's the key point about blocking is if we simply mixed up these 15 pieces, then we might not be able to detect the difference between these stress levels. These differences, if any, would be clouded by the inherent difference in these 3 classes of lumber. Okay, so that's how blocking would be applied to this example. So for example, now I would randomly assign each of these treatments once to each of these pilot samples. Okay, so we randomly permute the order, and so suppose we assign, let's say, 3, 7, 9, 1, 5 like this to the first 5 pieces in the cheapest grade lumber, and then we do the same for the other 2. Okay, and so that's how we would do with the randomization in this example. Now, this is you can think of this setup as simply an extension of one that we've seen earlier, and that is when we did specifically 2 treatments. Okay, so now we see blocking with, in this case, just 1 replicate per block. So you see in each block and treatment combination, there's only 1 specimen being in each of those categories. Okay, so let's finish our randomization here. So let's say we have assigned some load levels like this to our 15 specimens. Okay, so we think of, in order to model this, we will simply extend a framework that we've already seen, and now we're going to put in multiple treatments and also blocks. Okay, so you see we've kind of laid out the data nicely here, and when we finish this experiment, we will have 15 observations, one for each treatment and block combination. Okay, and then from there, we're going to do our usual investigation as to whether there are differences among the treatments, and we're going to do contrasts and ANOVA and those things again. So we'll see all those how all those concepts play out. So before I scrub this off, I do want to write down the basic equation. So let me get rid of this title so I can start writing the model down. Okay, so what we're saying is that we're going to model the response. So we're going to call that y sub ij. Okay, so this is the response in the ith treatment and the jth block. Okay, so as before, we're going to model this as related to in this case, three ingredients. The first one, we think of the response as varying from an overall mean, which we denote by mu. And we're going to have an effect due to treatment, so we denote that as tau sub I for the effect of the ith treatment. And we're going to have a block effect, which we'll denote by beta subscript j for the jth block. Okay, and so that's the model fit to it. Of course, there is going to be variability associated with the response that is not explained by the model, and so we put that in as a residual term. So Rij, so that's the remainder. The remaining variability in the responses that is not explained by the model. So to apply it here, so we say that there is an effect for each block. So therefore this group, okay, so this group has has a strength adjustment which is parameterized in the model as beta 1. Okay, so beta 1 is applied to everyone in the first block, okay, and so beta 2 is applied to all these 5 pieces in the second block. And so therefore, this block parameter allows to control for the average strength of each of these 3 grade qualities of wood. Okay, and so therefore, that's the role of the blocking variable. Okay, so we see that we don't necessarily care about the innate differences between the average strength of these three grades of lumber, but putting in this beta parameter will allow us to more easily detect the difference between the treatments that we actually do care about. Okay, once we've controlled for the variability between these 3 grades of lumber, we can more easily then see whether there is actually a difference between these treatment levels within each grade of wood. Okay, so that's how this model applies to this case. So in this example, I would be 5 because we have 5 treatments, and we would have 3 betas for the 3 blocks. Okay, so therefore there's 15 responses here, 5 treatments times 3 blocks, and 1 replicate for each treatment and block combination. Okay, so I wanted to give you this example to set up this context. Okay, so now I'm going to start running through the math so that we can understand how to work with this model. Okay, so with this example done, let me get rid of that, and then now let's talk about in general with T treatments and B blocks. Okay, so this is our model with T treatments, B blocks, and 1 replicate for each treatment block combination. Okay, so in other words, I goes from 1 to t, j goes from 1 to b. So total sample size is simply the number of treatments times the number of blocks, because we have just one replicate for each combination. So n is t times b. Okay, so as usual, we have, let's define our notation. Okay, so we want, so the parameters. Okay, so mu is our overall mean. Okay, and just to remind you, the overall mean, we set that to be equal to the expectation of the mean of all the units. So in other words, mu is the expectation of y bar averaged over both subscripts, so y bar dot, okay, in our notation. Okay, and then we have the treatment means. So as before, tau I, which are the treatment effects, govern the difference between each treatment mean and the overall mean. Okay, so mu plus tau I is the mean in the ith treatment. Okay, so like the other models that we've looked at so far, this model is over-parameterized in the sense that since we want these interpretations, it leads to constraints. Okay, so mu plus tau I, that's the mean, so that means mu plus tau I would be the expectation. We want that to equal the expectation of the the mean of all the units assigned to treatment I, so y bar I dot. Okay, so all the replicates assume, all the units assigned to treatment I across all blocks, so averaged over all the B blocks. Okay, so that is the mean of treatment I. Okay, so it's nice to be able to interpret the model parameters in this way, and this leads to some constraints on the parameters, which we can verify by using the fact that these y bars are linear combinations of normals. Okay, so this leads to two parametric constraints if we work out this math and set this expectation equal to mu. So this leads to constraints. Okay, so the first one is a constraint on the tau, so the summation of tau I is 0, and then the other is a constraint on the block parameters, so the summation of the block parameters beta j is 0. Okay, so these constraints can be verified by working out the expressions for these two expected values. Okay, so those derivations are very similar to one that was on one of your earlier practice sets. Okay, make use of the fact that the y bars are linear combinations of normals. Okay, so okay, no questions so far. All right, so I am keeping a close eye on chat, so just jump in and type if you have anything to ask, and I will do my best to respond. Okay, so we're now going to do estimation for this model. We've set up the context. Okay, so now we need to estimate these parameters from data. Okay, so think back to our example. Suppose we now go and do this pre-stressing of wood experiment. Okay, we now observe 15 measurements, and we want to estimate each of these parameters. Okay, so let's go ahead and do that. So this is again a least squares optimization. Okay, so so to get parameter estimates, we use a least squares, constrained least squares optimization. Least squares with constraints. Okay, and so what that means is we minimize as a function of the model parameters. Okay, so we have mu, tau I, and beta j. Okay, and what are we minimizing? We're minimizing the difference between the observations and the model fit. So Yij, the expected value for Yij is mu plus tau I plus beta j. In other words, overall mean plus the treatment effect plus the block effect. Okay, so we put that in here. Mu tau I. Okay, so that's the expression we minimize for least squares, so subject to the constraints. Okay, so that's our least squares expression. So this can be done using a variant of Lagrange multipliers. Okay, so I will not go through those details here. It follows very similarly as in the other cases. Okay, so I will jump right to the estimates themselves, and yes, you should block what you can and randomize what you can't. Thank you for that reminder. Thanks, chat. Okay, so all right, so let's write down the estimates. One other thing I want to point out about this model is one of its limitations is that we're assuming all of these effects are additive. Okay, so it's kind of inherent, it's kind of built into this model. So in other words, tau I is the same treatment effect applied no matter which block you're in. Okay, and so this is assuming an additive effect. You simply take the treatment effect, no matter what treatment and block combination you're in, you just add up the two effects. Okay, so that's kind of built into this model. Now, later this week or next week, we will talk about models with interactions. Okay, and that's where we allow different factors to have an interacting effect. Okay, so estimates. Okay, so this gives the estimates. Okay, so we have mu hat, so that's the estimate of the overall mean. So that's estimated by the overall mean in your data. So little small y, because this is calculated based on the data. So the average over all blocks and all treatments of your observed data, y bar dot dot. Okay, and so we also have our treatment effect estimates. So that's tau I hat. Okay, so it's not entirely surprising that the estimates for your treatment effects is simply the difference between the treatment mean and the overall mean. So in our notation, this is the treatment mean y bar I dot minus the overall mean y bar dot dot. Okay, and then finally, we now also have the estimates of the block effects. Okay, so very much analogously to the estimates of the treatment effects, the estimate of the block effects is the difference between the block mean and the overall mean. Okay, so just keep track of the subscripts. Treatment mean, so this is tau I, so it's I dot, and this is j, so it's dot j. So this is remember the block is the second subscript, so that's how we can easily remember. It's I, and then j and j. Okay, so block effect is the difference between the block mean and the overall mean. Okay, so those are our parameter estimates. Okay, now we have also the residual variability, so I haven't talked about that yet, but in order to do the test, we need to also estimate the residual variance parameter here, sigma squared, after fitting the model parameters. Okay, so to do that, we need to count up the degrees of freedom in this model. Okay, and so to do that, let's follow the rules that we had for counting degrees of freedom. So let's do that here. We have okay, just adjusting the camera a little bit here. Okay. All right. Okay, so degrees of freedom. So the rule for counting degrees of freedom is to take the total sample size. Okay, so that's in this case number of treatments times number of blocks. Okay, so that's T times B. And now we're going to have to subtract off counting up all the free model parameters here. So let me put this in big brackets. Okay, so how many things have we estimated in this list of estimates? Mu hat, tau I hat, and beta hat. So let's count these up. So I estimated one parameter. There's only one parameter for the overall mean. Okay, and then now I have T treatment. So therefore there are T tau i's. However, there is a constraint on the tau i's. Okay, so the summation tau I is 0. So after accounting for the constraint, I have one less tau parameter that's considered a free parameter. So we have T with T taus, but one constraint, so subtract out the constraint. So this is how many tau parameters we need to estimate. And similarly for blocks, I have B blocks. Okay, so we have B betas. Again, the blocks have one constraint. Block parameters have one constraint associated with them. So I subtract 1 here. So that's the number of betas we're estimating. Okay, so that's how we count up the number of degrees of freedom. Okay, so we simplify that a little bit. Okay, so we have T times B minus, so we have minus T minus B. Okay, and then I have 1, minus 1, and then minus 1. So we have minus 1. Sorry, plus 1, excuse me, because we have a minus outside. Okay, so that's what it simplifies to. Okay, and after you look at this is something that actually factors out very nicely. Okay, so TB minus T minus B plus 1, so that factors very cleanly into T minus 1 times B minus 1. Okay, so now we have the model degrees of freedom, and what do we use that for? Well, we use that in calculating our estimate of the residual variance. Okay, so we need to use that for our computation of sigma squared. Okay, so it leads to the estimate. Okay, so we estimate the variability that's left over after fitting the models, sigma squared hat. Okay, so I do 1 over the degrees of freedom. Okay, so T minus 1 times B minus 1. Okay, and then what do I have here is, well, we have a term for what's over here. It's also known as the residual sum of squares. Okay, so let's just write it out in full so it's clear. So I need to sum over all the treatments and blocks, and we're going to do so we take the observations and subtract off what the model has fitted for them. So the same things we had in the least squares expression, mu tau I beta j with hats. Okay, so with the estimates. Okay, so that is the residual. This term, this double summation, is the residual sum of squares for this model. Okay, and so this part, if we actually simplify it a little bit, So if we actually plug in these estimates for mu, tau I, and beta j, we can simplify this down to a rather symmetric looking expression. So you can verify later that this simplifies to yij minus the treatment mean. Okay, so I got. Okay, and then minus the block mean. So y bar dot j, and then plus the overall mean. So that's what the expression in this bracket simplifies to this. Okay, so take the observation, subtract the treatment mean, subtract the block mean, and then add back the overall mean. That's what this thing in the bracket simplifies to. Okay, so I said this verbally earlier, but just to make sure you have it, I will write down this to make sure you have it. So this model assumes that you can simply add together the treatment effect and the block effect. Add together treatment and block effects. For any combination of them. Okay, so that's the setup of what we call the randomized block design model. Okay, so now we're ready to now move on to doing contrast tests and ANOVA F tests based on this version of the model. Now, the key new idea that I want to address first is associated with the sum of squares decomposition. Okay, so I will make some space for that here. So I have the model, and now we need to look at the sum of squares decomposition. So that's the key new idea that extends this model from the basic ANOVA model we looked at for completely randomized designs. Okay, so here, let's go here. So key new idea. How does blocking change change the sum of squares, which I'll abbreviate SS, decomposition. Okay, so to do that, I'll break it down into a couple of steps. Okay, so I cannot go back to the last slide, unfortunately, because it has been erased. I don't know if that was a serious question, but I can't do anything about that. But you can definitely go back later when the video is posted, and you can rewind through to get anything you missed. Okay, so let's start with the result that we saw from completely randomized designs. So we know from so CRD for completely randomized design. Okay, so I'm going to rewrite the sum of squares decomposition that we had there and apply it to this case. Okay, so when we did the sum of squares decomposition, we had R replicates. Okay, so now instead of R replicates, I have B blocks instead. So this first part will look exactly the same, except this index will be B instead of R. Okay, so we do 1 to T, 1 to B, and Yj. So this thing I'm writing down here is also known as the total sum of squares. Okay, so Yij minus the overall mean, y bar dot. Okay. So this thing is also known as the total sum of squares. So let me write that over here. So this. Okay, why is it called the total sum of squares? It's associated with the overall variability in the sample. In fact, it is 1 less than the sample size times the variance of all your data. Okay, so this guy is your total sum of squares. Okay, so so the only thing that looks different here is I'm summing to b instead of r. Okay, because we're using b for the number of blocks. Okay, so what did that decomposition look like? So let me rewrite it, and then let me explain the connection to what we're doing here. Okay, so we learned that the total sum of squares decomposes into 2 parts. So there's the sum of squares associated with the treatment, and then there's the one with the residual, and the cross term sums to 0. Okay, so this was the decomposition. So let me write this down as a reminder. Okay, so it's now b instead of r. Okay, but otherwise this is still the treatment. This is what the treatment sum of squares looks like. Okay, how to remember this is the treatment sum of squares? Because it looks at the difference of each treatment mean from the overall mean. Therefore, this is the sum of squares associated with the treatment means, or treatment sum of squares. Okay, so this guy was what we've seen earlier is called the treatment sum of squares. Okay, and so anything not explained by the treatment in the completely randomized design case is in the residual sum of squares. And so again, let's write what that looks like. So we have this double summation. Okay, again with b instead of r. Okay, so what's left over? Well, it's the difference of each observation from the treatment mean. Okay, so that's what's not explained by the treatment. So that's the residual sum of squares. Okay, so that was what we had before. Now let's add in what we have now because of blocking. So the key idea here, which I will say just to overview first before I dig into the math, is that the residual sum of squares that we saw in the completely randomized case is going to break down into, we're going to subdivide this second piece into two subparts. Okay, one of them is going to be the block sum of squares. Now that we've added a block parameter, and then the remaining part will be the residual sum of squares after accounting for the block effect. Okay, so that's just a heads up of what we're going to do. We're going to decompose that term. Okay, so let me just lay it out here for you. So now we have blocking. Okay, so I'm going to start with the total sum of squares. Okay, so it's here. Okay, so this guy is still the total sum of squares. Okay, and so we already have a term here for treatment sum of squares. Okay, so this part is still the treatment sum of squares. Okay, so now what I'm saying is where we're getting to is that there's now going to be a new piece, which is going to be the block sum of squares. So I'm just going to put an empty thing here because we're going to fill it in later. So we don't know what this one is yet. Okay, so this missing piece is the block, is what we're going to find out very shortly. That's the block sum of squares. Okay, the reason I write this piece down is what's the last one? Well, the last one is the residual sum of squares. Okay, now, did I already write down the residual sum of squares? Well, yes. What is it? Well, about 10 minutes ago, I wrote down the estimate sigma squared hat. Okay, so remember the thing that is the double summation that we saw for sigma squared hat, that is the residual sum of squares. How do you get the estimate for sigma squared? You take the residual sum of squares, divide by degrees of freedom. Okay, so we found the degrees of freedom, it was t minus 1 times b minus 1, and then to the right of that was a double summation, and that is the residual sum of squares. So actually, we know what that is already, so let's write it here. Okay, so we already know from the last slide, which is now erased, that the residual sum of squares looks like this. Okay, so this was where we saw it before. Take the observation minus treatment mean minus the block mean, and then add back the overall mean. So that was an equivalent way to write the residual sum of squares. Okay, so we already know that this part is now the residual sum of squares after accounting for blocking. Okay, so from here, all we need to do now is to identify what this missing block is. All right, so that's the setup, and that's the key new idea now that we've introduced blocking. Okay, so in effect, let me emphasize one other thing before it's erased. Okay, so this was originally the residual sum of squares if I do not have blocking. It looks like this. So what we're saying is now this residual sum of squares from completely randomized design is going to break down into two pieces. It's going to break down into a block sum of squares plus the residual sum of squares after accounting for blocking. Okay, so in other words, by putting in the blocking variable, you reduce the residual sum of squares, and therefore, because many of our hypothesis tests are based on the estimate of sigma squared, this should reduce the estimate of sigma squared, and by doing that, we can make it easier to detect a significant difference between treatments. Okay, so that's the key conceptual idea I want to drive home here. Okay, so the next piece is just math. I'm going to show you what is this missing piece here by decomposing the residual sum of squares over here. The question is, how do we get the new residual sum of squares? So this was the double summation that you would have seen last one slide ago. This is the thing in sigma squared hat. Okay, so sigma squared hat is this piece divided by the degrees of freedom. Okay, so that's where this piece comes from. All right, so now I just need to show you what this missing piece is, and we will do it by yet another sum of squares decomposition. Okay, so. Okay, so what we need to do is decompose the residual, so the old residual sum of squares. So we decompose the RBD, residual sum of squares. Okay, so it's right over here. Okay, so that was the RSS from randomized block design. Okay, so we're going to decompose it. All right, so we have one piece of what we expect here. Okay, and so we're going to use the same old trick again. So we want one piece that's going to look like this, and so we're going to add and subtract whatever we need to construct this piece here. Okay, so I'm going to add. In this case, I need to have this piece, so I'm going to just write it down and then see what we need to add back so that we've added and subtracted the same thing. Okay, so I'm going to copy this over. So okay, and still need my summation. Okay, so I need a piece here, so it's yij minus y treatment mean minus block mean plus the overall mean. Okay, so I'm going to need this so that when I square, I get this term here. Okay, and so what do I need to add back such that this part balances out what we have on the left-hand side? Well, okay, so I have a yij, that's good, that's over here as well. I have a minus treatment mean, I have that over here as well. But what I have done here is I've subtracted an extra block mean, and then I've added a y bar dot dot. Okay, so to balance the two sides, I need to do plus y block mean, and then minus the overall mean. Okay, so now I've balanced out the two parts. Okay, so so we know the drill here is to expand. Okay, so we're going to group these terms exactly as the way we would envision to get, in order to get a square term that looks like this. Okay, so we're going to group terms like this, and then expand. Okay, so so let's write out what that is. So the first piece is, okay, I need to go a bit more room. Okay, so the first piece is what is now the residual sum of squares, which is what we have down here. Okay, so this is now our residual sum of squares. Okay, and then the second square term is exactly what we have been talking about here, is the missing piece. That's the block sum of squares. So what is so at the end of this, what does the block sum of squares term look like? Well, now we know what it looks like. It's this second piece squared. Okay, so we have summation 1 to t 1 to b of the second square term. Okay, so this is therefore the missing piece that needs to go in here to complete the sum of squares decomposition. Okay, so this is the block. Okay, so this is what we were. This is the piece that we have been looking for. Okay, and of course there's one little caveat, and that's to show, and that's to verify that the cross term. So we did a squared plus b squared. We also have a cross term 2ab. That should be verified to be 0. Okay, so let me just add that note here. Okay, so once we've checked that the cross term is 0, then we have completed this decomposition. Okay, and we can check. So the 2ab term looks like this. Okay, so it has this residual part times the block part. Okay, so that's not a particularly interesting calculation, so I won't do it here, but I will put this on a practice problem set to guide you through how to check. So it's really a matter of working through this double summation. Okay, so we have to check that this equals 0. Okay, so this will be in a future practice set. I will walk you through this calculation. Okay, so think it's a good time for a short break. So let me just change the setup here. Okay, so just give me a moment to set up the camera for the piano, and then we'll have a little musical interlude. Okay, so that was Chopin's Barcarolle, Opus 60. So just give us a moment and we will be back to our regularly scheduled programming. If you have other music requests, please write them for me in the comments below. Okay, let me just change the zoom and then we will be back to randomized block designs. Okay, where were we? Okay, we need to do hypothesis tests now. Okay, so we need a few distributions to do that, and they are distributions that are familiar to us. The normal, the chi-square, and the t distribution. Okay, so let me run through those real quick. So this was the sum of squares decomposition. All right, so I can erase this. Okay, so distributions. Okay, so we know from that the residual sum of squares is associated with a chi-square. So just to write it down for completeness, you take the residual sum of squares, divide by the true unknown sigma squared. That one follows a chi-square distribution. And what's the degrees of freedom? It's the degrees of freedom of the residual in the model. So we saw that before. It is t minus 1 times b minus 1. Okay, so likewise, let's write some distributions for the observations. Okay, so we know from the model that the observation of treatment I in block J is normally distributed by assumption mu plus tau I plus beta j. Okay, so that's a key model assumption. So this is a model assumption that it follows a normal. Okay, and so we also learned that we can take the means are also normally distributed. So let's do the treatment mean. And so that would be normal with its treatment mean, that's mu plus tau I. And it's averaged over all the block units. So how many of them are there? There's b of them, so this sigma squared becomes sigma squared over b. Okay, so make sure you know to show this. Okay. Okay, so now suppose we want to do a contrast test in this situation, and so okay, so for contrast. Okay, so theta has been our usual notation for contrast. So we can write that as summation. So AIs are the constants associated with the contrast, and they sum to 0. Okay, so there's a linear combination of treatment effects. Okay, so AI times tau I with yeah. So we need these contrast constants to sum to 0. Okay, so for contrast, we first have to estimate the contrast. We estimate with okay, so we plug in tau I hat. Okay, so we plug in the estimates for the taus, and then we simplify the expression using this constraint. So we've done this in the ANOVA case, and it's analogous here. Okay, so the estimate is AI times the sample mean in each treatment. Okay, so that's the estimate. And because this is a linear combination of normals, okay, so the treatment means are also themselves normal. We have a normal distribution. We view this as an estimate, as a random variable. Okay, with so theta, okay, so the random variable has mean, is normal with mean theta. In other words, it's an unbiased estimator. Okay, and so this is actually the same result as with randomized block design, except instead of R replicates, we have B blocks. Okay, so the sigma squared can come outside, and then we have in here the square of the constants and over B. Okay, so from here that's where we get the t distribution, because we can standardize. So we do subtract off the mean, divide by the standard error. Okay, so the square root of this expression, except we don't know sigma, so we plug in the estimator for it. So we replace sigma with the estimator, and then we have inside the square root the constants. Okay, so this is where we get a t distribution. Okay, so this is this is t. Degrees of freedom is the same one from the chi-square, so t minus 1 times b minus 1. Okay, so this t distribution is the one we use now to do tests of contrast in the case of this randomized block design. Okay, so this is used for confidence intervals and hypothesis tests of contrast. Okay, so that's the only change here. I'm going from randomized block design, from completely randomized design to randomized block design. You see this degrees of freedom in the t distribution changes. The way we estimate sigma changes because it now accounts for the block effects. And so now instead of replicates, we have blocks. Okay, so that's how we do contrast, tests of contrast in this case. So the last point for today is, well, how do we do ANOVA in this case? So we already did most of the hard work for that in terms of we already built the sum of squares decomposition, and so I'm going to wrap it up by giving you the ANOVA table for this case. Now, before I get to that, let me just quickly recap ANOVA and then apply it to the situation. Okay, so ANOVA, if you recall, tests the hypothesis of whether there are any significant differences among treatments. Okay, so for ANOVA, it's the same hypothesis here. We're testing. We test null hypothesis. There are no significant treatment effects. Okay, so tau 1, tau 2, up to tau t are all the same, and so in other words, if they're all the same and they sum to 0, then that means they're all 0. So it's the same hypothesis. Asking whether there are any differences among treatments. Okay, so the development is very similar. So let me just outline it for you, so you get to see it again. So when the null hypothesis is true, then it means when the null hypothesis is true, then that means the taus are 0, and so the treatment means simply follow a common mean, so normal mu sigma squared over b. Okay, so otherwise, if we're not in the null hypothesis case, then of course we would have a plus tau I over here. Okay, so that's what's true when we have when we're under the null hypothesis. Okay, so it's actually very similar to the completely randomized case. So similarly to CRD. We have the treatment sum of squares that can be written like this. I'm sorry. I already took out the b, so we don't need a double summation here. So just have b and the difference between the treatment mean and the block mean. Okay, so that's very similar. So this we define an alternative estimator for sigma squared based on the treatment means. Okay, so in this case, instead of R, we have B here. Okay, so this is also known as, so this part, just remind you, this is the treatment sum of squares. Okay, so when the null hypothesis is true, this part is related to a chi-square because we do not have treatment effects tau I. Okay, so in this case, then and so this treatment sum of squares, if you divide that by sigma squared, this is a chi-squared t minus 1. So that's this follows the same outline as how we derived the f-test for the completely randomized case. Okay, so now we have two chi-squares. We have a chi-square coming from the treatment sum of squares, and we have another chi-square coming from the residual sum of squares, and so this is where we get an f-test in a very analogous way. Okay, so the main thing we have to be careful here is make sure we use the correct degrees of freedom. Okay, and so the ratio of the chi-square scaled by the degrees of freedom is where we get the reference F distribution for carrying out ANOVA. Okay, so let's do it here. So treatment sum of squares divide by is degrees of freedom, that's t minus 1. And then the other chi-squared is associated with residual sum of squares. Okay, divide that by degrees of freedom. Okay, so now we have a ratio of chi-squares, so appropriately scaled by degrees of freedom. Okay, so that's the reference F distribution for testing this hypothesis. Okay, so there's an F distribution, degrees of freedom t minus 1 from the treatment, and you can easily read that off this expression because these the degrees of freedom in the F distribution are exactly the ones coming from the numerator and denominator chi-square random variables. Okay, so we have t minus 1 times b minus 1 here. Okay, so when do we reject the null hypothesis for ANOVA? Well, we reject when this ratio is large. Okay, why? Well, because when the null hypothesis is false, then this treatment sum of squares is going to be expected to be larger than the denominator. Okay, so that was something we found via an exercise in completely randomized design. The same logic holds. So we reject the null hypothesis. Okay, so when this when we look at this statistic, then basically we're okay. So we can rewrite just to prep for the ANOVA table. This treatment sum of squares divided by its degrees of freedom is another name for that is simply the treatment mean square. Okay, so we divided by t minus 1. So another way of saying this is simply the treatment mean square. So ms and what is this? Residual sum of squares divided by its degrees of freedom. So that's the residual mean square. And what is an equivalent way of writing that? Well, it's simply sigma squared hat. Okay, so that's how those things fit together. So there's a question in chat, which is, does the order of degrees of freedom matter? Yes, it does, because one of them corresponds to the numerator and the other one corresponds to the denominator. So you want to put the numerator one first. Okay, so t minus 1 first, and numerator first, and then denominator. Okay, so we reject if, oh, I forgot the if this ratio, okay, so this quantity, so this treatment mean square over sigma squared, just another way of writing this ratio. Okay, so when this is large, okay, so bigger than some constant, c. Okay, so where we look up the quantiles of this F distribution. So the probability in the reference F distribution, so the F with degrees of freedom t minus 1 in the numerator and t minus 1 b minus 1 in the denominator. Okay, so we reject if that F distribution is larger than that with probabilities equal to the significance level alpha. Okay, so so this alpha is for level alpha test. Okay, so that's essentially all the theory associated with the randomized block design. So the last thing I'm going to write down, and then we will close for today, is I just want to write down the ANOVA table. So everything, all the quantities we defined today will fit nicely into the ANOVA table, and so that would be a good place to wrap things up for today. Okay, so I'm going to remove this because I think the ANOVA table will take me the entire board. So. Okay, so here is the ANOVA table for the randomized block design, which we've been talking about. Okay, so on the left, I'm going to always start with the source of the sum of squares. Okay, so source and sum of squares, and then we have the degrees of freedom, and then the mean square, and then finally the F statistic. Okay, so again, the main new thing here is we're going to have an extra row because it's going to correspond to the block sum of squares which we saw in the earlier decomposition. Okay, so we'll have an extra row here. So let me write this down. So we have treatments. Okay, and then we're now going to have an extra row for blocks. Okay, we need some space here. And then residuals. And then everything adds going to add up to our total. Okay, so what are these sum of squares? Well, let's start writing down the treatments. Okay, so that's the sum over y, the treatment means from the overall mean. Okay, so I'm writing it here as just a condensed double summation with both I and j. But we know that we can sum over j because there's no j in here. So this sum does appear b times for a number of blocks. So it can also be written simply as b times summation over the treatments, like so. Okay, I can do a similar thing for the blocks. Okay, so the block sum of squares by definition is the double sum over the square differences of the block means from the overall means. Okay, and analogously to the treatment one, I can do the summation over I because there's no I in this expression. Okay, so in sum over I, there's how many times does it appear? Well, there are t treatments. So I can rewrite this as simply t times the summation over j. Okay, and then finally for residuals, well, that's the expression we've seen a couple times already today. It's double summation of the residual sum of squares. So it's probably the third time we've seen this. So it's the yij minus the treatment mean minus the block mean, and then plus the overall mean. Okay, so that's our residual sum of squares, and we've shown in the decomposition if we add up these three sum of squares, we get back the total sum of squares. And so let's just write the total sum of squares down here at the bottom. It's the double summation of all the observations compared to the overall mean. So this is associated with the overall variability seen in all your observations. Okay, so that's the sum of squares. The rest is pretty straightforward to fill out. Except it's a little bit misaligned now, so let me just move this. Okay, so we have the degrees of freedom. Okay, so now we just fill in the degrees of freedom we already saw before. So this is t minus 1 for treatment. Okay, blocks. Okay, so analogously to the treatment case, for blocks we have b blocks and one constraint. So that gives us b minus 1 block degrees of freedom. And then residuals is the denominator in the estimate for sigma squared. So it's t minus 1. B minus 1. And then the total is simply 1 less than the total number of observations, so t times b minus 1. Okay, so let me go over here and finish up the table. So we have mean square. So all I have to do for mean square is simply to divide each by the corresponding degrees of freedom. Okay, so this one is simply treatment sum of squares over t minus 1, log sum of squares over b minus 1, and residual sum of squares. If I do the residual sum of squares divided by the degrees of freedom, that's simply the estimate for sigma squared. So I can simply write sigma squared hat here. Okay, so that has the same role in this table. Okay, and then finally over here we have the F statistic, which as written right before this is simply to take the treatment mean square and then divide it by the residual mean square, which is simply sigma squared. Okay, so that is the ANOVA table for randomized block design. Okay, so that is it, and if there are any other questions, I will answer them in the chat. We will resume our regularly scheduled programming on Wednesday at the same time, and I will start off Wednesday with an example. So I'll finish up that lumber example and show you some real numbers to illustrate what we've been doing. Okay, and in the meantime, if you enjoyed today's content, make sure you smash the like and subscribe button so that you do not miss any future videos, which, we present content here that goes, beyond ideas, beyond disruption, and maybe even beyond statistics. So make sure you're subscribed. In the meantime, there is going to be a special episode on Wednesday morning, 11:30. I'll be giving a lecture to my other class, and I'm going to be talking about some spatial statistics and in relation to the COVID virus. So if you're interested, you can tune in again on Wednesday morning. Otherwise, I will see you same time, same place, Wednesday at 4 p.m. All right, so we'll sign off for today, and you all have a healthy and good rest of your day.